He is the Associate Lab Director of Energy Technology Area, that is ETA, at Lawrence Berkeley National Laboratory. He also happens to be an adjunct professor in the Department of Mechanical Engineering at UC Berkeley. Before Professor Ravi joined LBL, he was the Vice President of Product Development of Sheetak INC, a startup that basically deals with the development of thermoelectric energy converters and other stuff. Before this, Professor Ravi had actually completed his PhD from, BTech from IIT Delhi. I had some informal conversation, so just before the session started, that is where, and he completed his BTech from IIT Delhi and then PhD from Arizona State University. To his credit, Professor Ravi has published more than 100 archival journal papers and holds more than 35 patents. And he also is a fellow of ASME. And his research interests include applications of nano to macro scale thermal science and engineering in solving large scale societal problems such as GHG free energy conversion, storage, and transport. So it's our pleasure to host and welcome Professor Ravi for this keynote lecture of the day. Professor Ravi, please hand it over. I am handing it over to you.
Thank you so much, Professor Srivastava, and thank you everybody else who have organized this, and thank you for the kind invitation. As you have seen, I've changed the title a little bit, even though the theme is the same, because I'm also going to talk about a little bit of battery, not only thermal storage, because I think that's equally important. So the title of the talk is Operando Probing and Tunable Energy Storage, same as dynamic storage. And let me just start now. So I'll try to cover three things in this talk. One is thermal challenges and opportunities in electrochemical batteries. Then combined electrical and thermal storage. Then you combine electrical and thermal storage in one single system. And finally, thermal fluids with enhanced heat capacity, right? All right, so let's look at where electrification of where the batteries are used and what does it mean for in the future. So one of the biggest things that being seriously investigated is called extreme fast charging of batteries. So today, typically batteries, it will take at least here in the US, level 1 charger, it takes almost 30 hours to charge the full pack, and a level 2 charger, you can charge a pack in roughly 8 hours, right? But imagine that if you charge a battery in 10 to 15 minutes, right? That will be a game changer in terms of penetration of electric cars. Because today, when you fill petrol in your car, you fill petrol in a car in 5 minutes, right? That's what we are used to, and then that adds so much of flexibility in the overall system. So similarly, if you can charge a battery fast, that will be a really big deal in terms of increasing the penetration of electric cars. However, there are some challenges. When you increase it to 15, decrease the charging time to 10 to 15 minutes, the power, so if you can look at here, the time to charge dramatically decreases, let's say, 15 minutes, but the power is huge. It goes almost of the order of 300 to 400 kilowatts you need to pump into the battery pack. So there's going to be a lot of thermal challenges. You'll be generating a lot of heat as well while doing that. So that's one big opportunity. Another one is that the future belongs to high energy density batteries. For example, there's a lot of interest in electrifying aircrafts, particularly maybe short duration aircrafts, right? But again, you will need higher energy density batteries, because otherwise, if you low energy density batteries, it's just going to be add a lot of weight to the aircraft. And at the same time, same thing, you cannot wait for an aircraft to get charged in 8 hours, and that's going to be a very, very bad business proposal for airline industry. So they would like to have fast charging there as well. So combination of high energy density and fast charging provide some unique opportunities in thermal science, right? So there are two challenges when you do extreme fast charging. So what happens is that the way a battery works, lithium-ion battery, that you have a cathode, which is, let's say, lithium nickel cobalt oxide cathode here. And when you're charging the battery, the lithium moves from the cathode side to the anode side, and anode is typically made of graphite. And the lithium goes and sits between the graphitic planes, right? So nicely it goes and nicely sits. That's called intercalation. Okay. But the problem is that when you do extreme fast charging, so the chemical reaction is happening so fast that the lithium, rather than intercalating, cannot diffuse fast enough, right? So you start to plate right here. It doesn't insert, you just start to plate, right? So that's a major challenge. And second is enormous amount of heat generation, right? As I mentioned earlier. So if you look at a battery, although the previous picture was very simple to explain the physics, what's going on, in reality it's a much more complex system, right? So you start with the pack level, and you have thermal management. Typically, fluid goes in, some kind of a coolant. For example, if you have a Tesla car, Tesla uses liquid cooling, right? And then inside is a very composite structure. You have the cathode. It's not a simple lithium cobalt oxide. It's basically embedded inside. It's like a composite. It's like you have the active material, which is the cobalt oxide material. Then you have a binder which binds it together. Then you have carbon black, which takes the electrons out or in, depending on the charging or discharging, right? And then you have empty pockets where the electrolyte goes in. Same thing happens on the anode side. So if you zoom in here, the very interesting physics happening. You have solid state diffusion of lithium happening inside this, say, this is a graphite anode. So lithium is diffusing in, right? That's happening. Then you have something called solid electrolyte interface growth right at the interface, which is not very desirable. And depending on how fast you're charging, lithium may not be able to diffuse inside, is plating, okay? So the temperature has very interesting effect. On one hand, it increases the intercalation kinetics, okay? So if you have higher temperature, because solid state diffusivity increases. So in a way, for extreme fast charging to avoid plating, you may want to increase the temperature. However, when you increase the temperature, it also increases side reactions and also increases the SEI growth, right? So when you're discharging the battery, you want to bring the temperature down, right? So it's possible that optimal temperature is different for charging and discharging, right? That offers a very unique opportunity in terms of thermal management. And at the same time, you got to understand particles to system level thermal understanding is needed. As you can see, it goes from, it's not simple, it's like a composite structure. And then you also need a coupled electrothermal model for extreme fast charging is critical, right? Because electrochemistry and temperature and heat generation are coupled. So one other thing we recently did was we started looking at that, okay, when you fast charging, first of all, as I mentioned earlier, extreme cases is plating, but even with moderate fast charging, you can start seeing non-uniform diffusion of lithium inside the anode, okay? So let's say here is the anode and the lithium is going in, right? So as a function of Z direction, Z, you will see the thickness, you should see that the lithium is not uniformly deposited. And 1C charging means that you're charging the battery in 1 hour. 0.1C means that you're charging the battery in 10 hours, okay? Just look at that way. It's inversely proportional to the charging time. So the pristine, this is the graphite, it looks completely black. 0.1C charging, as you can see, changes the color, but it's almost uniform color. This is just a current collector. 1C, that means I charge it 10 times faster. You can see this is much more gold-like here and much more black here. That means there's a concentration gradient, right? And people have observed this concentration gradient using X-ray diffraction, right? This is a paper which shows X in lithium XC6 as a function of Z, the Z direction, and depending on the state of charge, there is a significant concentration gradient, right? So the question was that we started asking, can we detect this concentration gradient operando? That means in an actual cell while the battery is working, right? So that if you look at, it's very interesting. The thermal conductivity of these materials is a very strong function of the lithium concentration, okay? So for example, in the typical lithium carbon electrode, which is the graphite, which is used in lithium-ion battery today, the thermal conductivity actually decreases as the lithium concentration increases for the graphite. Because what happens is when this is graphite, the parallel planes, lithium comes in, right? It changes the lattice constant. That means it changes the the phononic behavior, which are responsible for heat conduction, and that changes the thermal conductivity. So that is the phenomena that we started thinking that, okay, that means if I can measure the change in thermal conductivity, I can back calculate the lithium concentration, right? So we use something called thermal wave sensing, which is pretty well known in thermal communities, also known as 3 omega technique. What you do is you have a sensor here, a thermal which is sending sinusoidally, you're heating it, okay? So you're passing a sinusoidal current. So, and the frequency, you can do a frequency sweep. And the thermal penetration depth, right? This is basic heat conduction, right? The thermal penetration depth of this thermal wave is inversely proportional to the square root of the frequency. So that means if I have a higher frequency, the wave is focused here. If I have a lower frequency, the wave penetrates deeper inside. So I can really probe the different layers or as a function of thickness, what's happening, right? And this is actually we're putting a sensor in an actual battery. And this is, first of all, we also wanted to make sure that the battery still works like a battery. So here's the discharge capacity, cycle number, and there's no change with the sensor and without the sensor. Then, first of all, what we did was that we did a slow charging of the battery. Okay, very slow. As I showed you, the concentration is uniform, right? So this is state of charge. 0 means pure graphite. Okay, no lithium has gone inside. And then 0.1 C means we are charging it very, very slowly. And 3 omega is the signal from the sensor, right? State of charge, 20% means that 20% of the battery is charged. State of charge, 100% means 100% of the battery is charged now, right? And you can see that the signal is changing dramatically, right? So from here, by fitting a thermal model, we can figure out that how the thermal conductivity of the anode changing with the state of charge, okay? Which basically means that the more and more lithium going in, and the thermal conductivity is decreasing, okay? It goes back to this behavior that I mentioned earlier here, if you can see it, right? So now I have the K anode as a function of state of charge. And then we also compared that with some molecular dynamic studies, and then they match very, very well. Okay, so this is right here, comparison with molecular dynamic studies, right? So this curve here is our calibration curve, right? I know how K anode, thermal conductivity, the anode is changing with the state of charge. Once I do that, now what I do is that we do a very fast charging, and then we do the same thermal wave measurement at fast charging, 10x, right? 1C, which is 10 times much faster than 0.1 C. And then again, we compare the ratio of the 1C versus 0.1 C, and you can see a big difference depending on the frequency, right? By fitting a model, now I can back calculate the K anode as a function of Z, okay, for different states of charge, right? So I have now K anode as a function of Z, and then you can see K anode here. This is I know from this K anode here, and this K anode as a function of Z, I can map them together and exactly figure out local state of charge. So even if the average state of charge is 70%, but this is a concentration gradient. So the average of this is 70%, but highest is 90% here, and the lowest is 60% here. Why is that important? Because all the things, plating, safety, and all the things depend on local concentration of lithium, right? When something catches fire in a battery, that depends on local concentration. So it's very important. So by using the thermal wave sensing, we can actually, probe a real cell and figure out what is the local state of charge. And that can be really, really useful in terms of monitoring the health of the battery. All right, that's one. Let me switch gears a little bit. The heat that is generated in the battery itself, right, is very, very important. That's why we do thermal management. Now, the question is that when you do fast charging, are there some other phenomena in the heat generation becomes very, very important, right? So if you look at, when you mix things together, there's something called enthalpy of mixing and entropy of mixing. Typically, we ignore the enthalpy of mixing. But here there is such a huge concentration gradient when you're doing fast charging that you cannot ignore enthalpy of mixing. So the Q, the heat that is generated in a battery, there are many terms. I'm not going to bother you with the equation here, but just look at here. One is a reaction over potential and a transport loss just because of finite thermal electrical conductivity, finite ionic conductivity. So that's, you can consider this as a Joule heating as well as the reaction over potential. Then entropic heat, which is basically reversible. Then heat from side reactions is a chemically reacting system. And there's something called heat of mixing, right? Which comes from enthalpy of mixing. Most of the models, they ignore it, the heat of mixing. And the models that try to include the heat of mixing, they assume the concentration gradient is very, very small. So they use a Taylor series expansion. But as I showed you earlier, even at 1C, there is a huge concentration gradient. So we cannot ignore heat of mixing. So anyway, we recently calculated it, and we found out that at very high C rate or extreme fast charging that I mentioned earlier, the average contribution of heat of mixing can be as high as 20%, which is a huge number. So something to keep in mind, that heat of mixing has to be considered while you're calculating heat generation in extreme fast charging cases. All right, moving on. The future of batteries is you may have heard, is called solid state batteries. Okay, and solid state batteries is basically, currently the lithium ion battery uses a liquid electrolyte. In solid state battery, the electrolyte gets replaced by a solid electrolyte. Okay, which is much more safer. And then instead of a composite graphite anode here, you just have a lithium anode here. Okay, so now you can zoom in here, and if you zoom in into interface, this is a very complex interface. Okay, and there's a lot of problems right now people are trying to solve, and that leads to a lot of different challenges electrochemically. So almost like, I spent my early career after my graduate school at the chip making company Intel, and I did electronic schooling. So I really looked at a lot of interface materials and interface phenomena in chip cooling. So just realize that, okay, the lithium metal solid electrolyte interface is very similar to a chip in contact with a heat spreader, right? So you can calculate the contact resistance, which depends on the nominal area and the real area. Real area is smaller because you have voids, right? So now again, we are doing this thermal wave sensing, calculating this, measuring this contact resistance directly from the thermal wave sensor. And this area, A nominal and A real, depends on pressure. We're seeing that this contact resistance changing with pressure. We're also changing some very interesting behavior with cycling. So we are hoping that with this technique, we will be able to uncover a lot of electrochemical phenomena at that interface. And particularly, we will be able to calculate this actual A nominal and A real and feed that in the electrochemical models, right? All right, so let me moving on. Heat thermal storage, right? So energy storage for heating and cooling. Building heating consumes roughly 75% of electricity in the United States. Building cooling is on the rise in the world. I mean, in India, there's so much growth of air conditioning, right? Then in the Western world, where it's more of a heating climate, building heating will get electrified using heat pumps and / Joule heating. So therefore, cooling plus heating is expected to be more than 50% of electrical load in buildings, right? So recently we asked a simple question. This case study is for United States, but the methodology equally applicable for rest of the world as long as the data is available. That if let's assume that you have 100% renewable energy grid, electricity is coming from 100% from renewable sources. The results I'm showing you for 50% solar, 50% wind, but we have done it for the all the way from 100% solar to 100% wind. Okay. So the question we asked is, how much energy storage, doesn't matter where you put it, doesn't matter whether it's electrical, thermal, or whatever have you, how much of that energy storage will be required to just support heating and cooling of buildings? Okay. So what we found out, as you can see, first of all, the black line is the supply curve. So that is the supply of electricity. No wonder it peaks at around noon, because this is 50% solar, 50% wind. The gold is the non-thermal load in the building, right? And the red is the thermal load. And you can see in the shoulder areas here, the shoulder hours here, you don't have any electricity available, but you have demand. That's where storage becomes very important, because you have extra electricity available here. In the winter time, we did the same thing for heating. Same challenge here. You have heating requirements here, but you don't have any electricity available, right? But you have a lot of electricity available here, so you can do storage. So from there, we calculated for all these different scenarios, how many gigawatt hours of storage will be needed just to support thermal loads in buildings. And we found out that, I mean, we did a sweep, but roughly of the order of 2,500 gigawatt hours. That's huge. That is roughly equivalent to 50 plus million electric vehicles, 200-mile range, right? That's a huge number. So now the question is whether you want to store the energy in electrical form or you want to store the energy as a thermal storage, right? So we analyzed 3 scenarios. One is an HVAC system, an air conditioning system where you have a lithium-ion battery, you store the energy in the battery, and then you run the HVAC whenever needed, versus you run the HVAC but store the energy in thermal storage. Okay, there are 2 ways to store the energy. One is you just have a box which stores all the energy right here, or maybe you can distribute the storage in the walls of the building. Okay, because you have this plenty of area available in the walls of the building, right? Anyway, we did the analysis. We found out that thermal storage can be much, much economical than lithium-ion battery. I'm just going to talk about one of the ideas, this distributed storage in the envelope. Okay, so there's so much of area. For example, in the US, a typical 2,000 square foot house building can store roughly 44 ton hours, which is roughly 150 kilowatt hour thermal energy storage. This is roughly equivalent to 9 hours of cooling, assuming 5 ton cooling needed. Okay, but we have a lot of area available, but once you store the energy, problem is that there is no perfect thermal insulator, so it leaks, right? That's why you also need a thermal switch. Just like electrical switch, can be also a thermal switch. So these are 2 areas we are working on. Another area, important thing is that, when you store it in the walls, for example, you want the battery, the thermal storage to be used all year round. So you want to store heat in winter time, and you want to store cold in summertime, right? That means, let's say your 25 degrees is your temperature, but in the winter time, you would have to store it higher temperature, 30 degrees, and then in the summertime, you have to store it lower temperature, right? So that you can store cold. So that means, ideally speaking, you want a tunable transition temperature material. Can you tune the melting temperature? Let's say you're using a phase change material. So we recently figured out a way to tune it actively by using salt. As we know from high school physics that you put salt in ice, it changes the melting temperature, right? The challenge is how do you do it dynamically so that you can continuously tune it, right? So we use this methodology here. We have a salt, and then we charge and discharge, and we can dynamically tune the transition temperature. And as you can see that we have tuned it by 6 degrees by changing the voltage. At the same time, we can also store electrical energy in the same system. So this is a tunable thermal plus electrical storage system where you're basically storing both electrical and thermal energy at the same time, and you can also tune the transition temperature where the material will melt. All right, I'm going to change gears. I have a couple of minutes left. On a thermal fluids, we know is very, very important for both heat transfer and storage. Microelectronics cooling for your computer. There's a lot of interest in using liquid to cool the computer chips, particularly with all the load because of artificial intelligence and machine learning. Battery, this is the patent for Tesla car. They have this kind of a system in the car. They use ethylene glycol water mixture. Transformers, they use mineral oil. There's also a lot of stuff in storage, storing heat energy in the liquid itself, right? So as we know, heat transfer and storage density is directly proportional to heat capacity. But here's a challenge. Most of the thermal fluids are van der Waals bonded molecules. So they're less than 5 kilojoule per mole. So they have very low heat capacity. Mineral oil has a very low heat capacity. Thermal has a very low heat capacity. Water has the highest heat capacity because 70% of the heat capacity in water is because of hydrogen bond breaking, 10 to 30 kilojoule per mole. However, as we know, water freezes 0 degrees and boils at 100 degrees. So the question is, can we use covalent bond breaking, which is like 100 kilojoule per mole, to beat water or achieve high heat capacity for temperature greater than 100 degrees Celsius? So we have recently investigated something called a Diels-Alder reaction, where you can actually get a meaningful result meaningful reaction at a moderate temperature, not a very, very high temperature, and then you can do reversible bond breaking to store energy and release energy. And here's the data. As you can see, the heat capacity for limited temperature is also higher than water itself. It is definitely much, much higher than other liquids. And also the viscosity is much better than other liquids and only 3 times higher than that of water, right? So this is very good. We also compared with we developed a model based on density functional theory predictions, and the DFT matches, where from the DFT we can actually predict some of the transition still enthalpy and entropy and the reaction enthalpy. It matches very, very well with the data. So it gives us a tool now to design molecules at will. And here is one result, for example, based on the DFT predictions. We are designing new molecules where I can exactly tune where the peak heat capacity happens, right? With that, I'm just going to end and we'll be happy to take questions.
Yeah, so thank you, Professor Ravi. Sayan?
Sir, we'll wait for 1 or 2 minutes for the questions to come from the portal.
Right. Yeah. So in the meantime, Professor Ravi, if I had a couple of questions or curiosity kind of this thing. So when you talk about this this possible solution for this thermal storage or thermal leakage solutions that you are tuning this thing. So I mean, with what accuracy and at up to what level of accuracy you can have this tunability, so that you can quantify that, okay, this is this much is the reduction in the possible thermal leakage from the wall buildings and those possible solutions.
Yeah, I mean, I think I will, let me just go here.
Yeah.
Sorry. Yeah, so I mean, basically, like here, right? I mean, this is we measure this in a DSC, which is plus minus 2 degrees, 0.2 degrees is the accuracy. Okay, so we can see that it's way beyond. But when we are also developing a switch here, which I didn't show you. Yeah, I didn't talk about the switch. We are developing a switch. We are actually in the process of submitting the paper, where we have shown that the switch, the ratio is almost 20:1 in terms of the conductance of the switch. So it's completely insulating when it is off state and very conducting in the on state.
Mm-hmm. Okay, and one question, I mean, I had from that that interesting technique of that thermal sensing, where you are actually calculating the quantifying the thermal conductivity.
Yes.
So the thermal conductivity would be is a strong function of the local distribution of local concentration of lithium.
Yes.
Yeah. So now with this, what you have talked about is some bulk or some average value for the thermal conductivity, say K anode, and depending on the concentration of lithium at a given spatial location with respect to the spatial distribution, how accurately you would be able to predict the spatial distribution of the thermal conductivity?
Yeah, but that's a great question, by the way. So that, as I showed you, we are able to predict it with a fairly, here's the error bar. Okay. So you can see that we actually resolved the spatial distribution. I think your question is, so you can say we cannot do more than 10 microns spatially. Okay. 10 microns is I would say is the resolution. That's why you can see the data is almost every 10 microns, right?
Right. Okay.
Yeah. So I think that in that sense, 10 microns is probably the best. With this technique, we have another technique in work which you can actually go to nanometer scale.
Okay, sure. And you have shown the dependency on the frequency, that it basically the penetration depth is inversely proportional to this. Are there any other factors also that actually?
Oh yes, absolutely. I mean, this was just to explain the physics, but you basically solve the whole transient heat conduction equation, right?
Okay.
For a sinusoidal heat source, right?
Right.
That's what you're doing essentially, and then you're basically fitting a model through that data that is coming as a function of frequency sweep. Like, look at this. We are going 100, almost 3 orders of magnitude frequency sweep. Okay, so the penetration depth changing with a huge margin, right? But you have to fit a whole thermal model through it to extract all the information out. Yeah, and this is actually, we published the paper recently, so it's there. A lot of the details are there in this paper.
Surely, this looks very interesting actually, and
this is very interesting because a lot of electrochemistry people have liked it too. It's a very different way of providing some electrochemical information.
Surely. Yeah. In the meantime, Sayan, are there any questions on the portal?
Yeah, one audience has asked, can you please suggest some potential research areas in thermal management of lithium-ion batteries?
Yeah, I mean, I think it's very right? As I said, extreme fast charging is one of the best ones, I can tell you, right? Because, on one hand, you want good temperature because to avoid lithium plating. At the same time, you got to discharge the heat when you're discharging the battery, right? So that's a really, really big, whoever can solve it, you can have a really good research as well as probably you can make money. You can have a company too. So that I think is everybody's struggling with that. Right, that's a big one. In fact, using the chemical information, figuring out a chemical information is a big one. I would say solid-state battery is another really, really big hot topic. I mean, everybody's struggling right now to make a solid-state battery work. It's all at the interface. So, and if you can thermally probe certain things and maybe provide that information to solid-state people, right? So this is. My main thing will be that my main guidance to any student in particular would be that be an enabler rather than just trying to say that I'm just going to do the thermal management for you, right? Because it's a battery at the end of the day. So if you can, like what we are showing with the chemical information, that's what the battery guy is like. Oh, okay, you're not telling me now how the lithium is doing, right?
Right. In fact, this interfacial transport brings in its own challenges. I mean, that is completely an open field.
Yes.
Just for, Sayan?
Yeah, Professor, there is a question from Abhishek Singh. He asks that for the tunability of PCM melting temperature, are you varying concentration of salts time to time? Or what other options to tune it?
Yeah, of course, there are other options to tune it too. People actually have tried pressure. There's barocaloric materials, right? Magnetocaloric material, barocaloric material. But the problem is you will need ginormous. It's like almost an order of gigapascal, maybe not exactly gigapascal, 500 megapascal and stuff. Then you can tune the temperature by. Here we are doing by 2.5 volts, like minimal, right? Lithium-ion batteries 4 volts, right? So there are other methods. I mean, I think if you look at this paper, we have mentioned some of the other methods, but unfortunately, I think those methods require significantly larger stimulus. Yeah.
Right.
Yeah, hello, sir. There is a question from Ashish. He's asking. Okay, sorry, sir. This has been done already, sir. It is coming again, sir. Sorry. No other questions, sir. Yeah.
Okay. Yeah. So, Professor Prasher, so sorry for these multiple questions. So,
no, go ahead. No problem.
I was just curious. With the current state of these batteries, like the main target or the challenge that as you have rightly pointed out, is the time that it takes for charging. So what do you what do you think? I would like to hear from you your views regarding how fast it can be made with the current technology and the current advancement that we are having in these technology. So how much time may still be reduced as far as the battery charging is concerned with all these newer developments coming up in this field?
I would say, like I have a car and then they give me fast charging, ramps up. It ramps up initially at 1C, okay? Then slows down. So first 60% is at 1C, okay? And then again it starts to taper down, right? So if you do complete, I think to get to 80% of charge, right, probably you can still do with 1C, okay? Which is 1 hour to 80%. After that, it's a completely slow down, okay? They just cannot. So I think at best case, 80% at 1C, right? Okay. That's just straight out. We right now have some data now coming out. We are in the process of writing the paper up. We have some ideas where we are able to show 6C, but that I'm not at liberty to discuss right now. But yes, but I won't call that state of the art. That's research still, right? But
Sure.
state of the art, as you asked, is Professor Srivastava, that is 80% up to 80% max at 1C best.
Surely. Yeah. So, Sayan, any other questions?
No, sir. There is no other questions as of now.
Okay. Yeah. So, if there are no other questions, I mean, we would like to thank Professor Ravi Prasher on behalf of this entire organizing team for this wonderful talk on this thermal storage, and then the challenges that we are currently having in these batteries in the context of electric vehicles, and it was a good mix of a lot of sub processes where you have very nicely included some of the advanced or some of the interesting say measurement technique for thermal conductivity in this context, leading to going into this flow and thermal transport in these battery systems, including the thermal storage and the related challenges. Thank you, Professor Ravi, for this insightful talk. And I think this is a great start of the day. Once again, thank you very much for.
Thank you very much.
Yeah.
I really thank you for the invitation. Thank you.
Thank you very much.
It's late
Professor
night for
Ravi.
me. Yes.
Hello, sir.
Professor
Yes.
Ravi.
Yes, sir. From organizer side, we have we'll like to inform you, we have different sessions going on from 10:15 a.m. So if you would like to join those session and see the
Right.
proceedings, we'll
I would love to, but it's all 8:15 here almost, okay, in the night.
Okay, sure thing, sir. Thank you
All
for
right.
joining us.
Yeah, Professor Ravi, thank you very much for your time. So the thing is that now we'll be having some oral presentations from the students. These are pre-recorded videos. So, and then that would be followed by question answers. So once again, thank you very much, Professor Ravi.
Thanks for that.
Yeah, thank you. Thanks a lot. Sayan?
Yes, sir.
Yeah, so I think it went all right.
Yes, sir. It went very fine, sir.
Right.
Our next session, oral presentation session, you will session chair for our
Right.
energy and environment session. It will start from 10:15.
Yeah.
So yes, sir. Sir, there will be 9 papers today.
Right.
9 presenting authors. So our session will be from 10:15 a.m. to 12:30 p.m. So, and each presentation will be of 15 minutes.
Right.
So, and actually, sir, there is a lag between the Zoom and the live webinar, like the live telecast. So it might take some 1 minute for someone typed a question and it will come to the Zoom question answer session. We'd like to request you to take the questions after each presenter, and you can ask your questions. And
Yeah.
we have already sent you the evaluation sheet, sir. So after each presenter is presented and every question is done,
Right.
and I will read out the name of the each presentation after you have finished your question answer thing after every presentation, and then we'll start playing the videos, sir.
Yeah, so basically it will go like this. So once these are pre-recorded videos.
Yes, sir. Yeah.
And once the video is over, you will take, I mean, if there are any questions, it may take about a minute or so to reach you.
Yes, sir.
Yeah.
And before that, sir, you can ask any questions you want to
Yeah. In the meantime, I will keep the presenter who would be present in the Zoom meeting.
Yes, sir. And after the question answer for each presentation is over, then I will announce the name of the next presenting author, presentation, and the affiliating institute, and then we'll continue like this, sir.
Surely, sir.
Okay.
Great.
Thank you, sir.
So we have another about
more than half an hour, sir.
More than half an hour. So this keynote was just half an hour or what?
It is like that, sir. Actually, there is actually after that, sir, there is it was 9 till 9:45.
Right.
Yeah, and after that there is a ComSol sponsored talk, and after that in between now is a sponsored talk is there, sir.
Okay, sure. Okay, so then we'll meet at some around 10 or so.
Yeah, sure, sir.
Okay.
Sure. Thank you, sir.